Hi, everyone. Good morning or good afternoon. Welcome to this session, Unleashing the Hydrogen Opportunity, the Key to Hydrogen Competitiveness. Thank you so much for joining today. My name is Christina Galan, and I'm one of the event producers at ATA Insights, where we create Red Mat events. As I said, thank you so much for joining today. We'll do a couple of housekeeping points, and then we will move on to the webinar itself. This session will be recorded, and it will be available to you in a couple of days. We will send it to your email. We will also send you the materials of the speakers. You also have a chat to let us know where you're from, what's your business, what you're interested in this webinar. And there's also another box that's a Q&A box for you to send any questions that you might have for our speakers. There are some submitted questions, but pre-submitted questions. But if you have questions that you would like to ask our speakers at the end of the session, please use our Q&A box. For those on YouTube, you can use the chat for your questions, but also let us know where you're coming from and what's interesting for you in this this webinar itself. So without further ado, let's start with the session. So as you know, hydrogen is expected to increase significantly in the coming years, and storage is going to play a key part in it. But there's also some challenges and opportunities there. So that's why we have these two amazing speakers. I will ask them to introduce themselves briefly, and then we will move on to the presentations, and finally end with the Q&A session. So I'm going to ask David Bentley from Ardent Underground to make a brief introduction of himself, where you come from. He's coming all the way from Australia, so it's pretty early or late for him, depends on what you're thinking. So David, welcome to today's session.
Thanks, Christina, and hello to everyone, and appreciate you joining. Yes, I'm coming from Sydney, Australia. I'm the CEO of Ardent Underground, and we're a company that's developing large-scale hydrogen storage in underground engineered cavities. So, I look forward to the rest of the presentation.
Awesome. Well, thank you, David. Thank you for joining us today. And we also have Sean Niknezhad from Texas A&M Energy Research. He's a postdoctoral associate. The Energy Institute, not Energy Institute. So thank you, Sean, for coming today, and welcome.
Thanks a lot. My name is Sean, as you mentioned. My undergrad was from London, and then I moved to the US 10, 12 years ago, working in energy industry. It's my pleasure to be here today.
All right, perfect. Well, thank you so much, both of you joining. I know that these presentations will be very interesting, so I think we can start moving on with them. So David, as you will start, I'm going to ask you to share your screen, and whenever you're ready, we can start your presentation. I see in the meantime that there are a lot of people coming from different places. So we have Nigeria, California, London, India. So it's great to have a global audience today.
Okay, great. Can you see the screen?
I know I can't see the screen yet. There you go. Yeah.
Okay. So, what this presentation is going to be about hydrogen storage and really some different methods, but ultimately we're going to concentrate on compressed hydrogen gas storage. Get some control here. So the outline of the presentation is why do we need storage? We're going to touch on some challenges. It's a difficult gas to store in some respects, and furthermore, the different categories, some options and design considerations, and then finally, I'll just give a really brief example of what sort of capacity are you going to need for hydrogen storage? So ultimately, what our company is trying to do is put a decouple intermittent renewable energy production from downstream supply. So regardless of what you're going to use your hydrogen for, there's always going to be this intermittent supply or unreliable supply from renewable electricity. Yet every single application you can think of is going to require some sort of on-demand requirement. Therefore, storage is pretty essential. And we make this bold statement that there is no green hydrogen application without hydrogen storage. And really, if we're going to look at renewable energy in the growth is going to be in solar and wind, really, unless you've sort of got hydro or geothermal energy making your powering your electrolyzer, well, you're going to need some sort of storage. That brings us to, what's the difficulty now? People have been storing hydrogen for a very long time, but what's changing now is the fact that we're going to need a hell of a lot more of it. Hydrogen typically used in industry today is made using the steam methane reforming process, and that's an on-demand system. So you make your hydrogen and then you use it. Whereas if we're going to make green hydrogen and replace that grey or black hydrogen, you're going to need to be able to store it. Now, with pressure vessels, this is the go-to situation, but they're very small and they're quite expensive. And so we really need to find better ways to store it. I won't read through all of those dot points there. I'm sure most people would probably understand that it's a very small molecule, leaks through things, is highly volatile in terms of its flammability range is very high. So what we're really going to need to get to this green hydrogen economy is safe, low cost, large scale storage. And we're going to need to be able to build it where it's needed. There's two broad categories of hydrogen storage. We have our material-based storages, and they're things like nanotubes people are working on to try and physically get more hydrogen into a smaller space. And then there's the range of chemisorption options. So these would include ammonia, which I've shown there, obviously, but other types of liquid hydrogen carriers, or even indeed solids with metal hydrodes and things. And then there's the physical systems. I'll just sort of mention each of these systems on the material base will require some sort of treatment to get the hydrogen in and or out. So that will be catalysts or thermal energy or something. On the physical side, we don't change the structure of the hydrogen. It just stays as hydrogen itself, H2. And we compress it. Which is simply in the simplest form as, volume 1, pressure 1 is squeezed down to volume 2, pressure 2, we get more energy in the smaller space by adding compression energy. And then we can take it even further at a hell of a lot more energy and bring it down to a liquid, which is at minus 253 degrees C. The problems you sort of have with that is certainly heat leakage into it, boil off, and just storing things and handling things at cryogenic temperatures become sort of problematic. So the rest of this presentation, I'm just going to talk about the very simple way of compressing gas and putting it into storage. These are the sort of systems that are available today, and you can probably familiar with them. We see our tube trailers, which are becoming quite popular. The tube trailers over here can hold a maximum of about 500 kilograms. I believe in Europe they're going to be a little bit bigger than that. But it gives you a perspective of sort of what you can do. And I've sort of put an arbitrary number there that, once you want to store, if they're great to store up to about 10 tons. the way they're configured, and certainly there's opportunities to store more. The pipeline down the bottom, particularly if you have to get the hydrogen from one spot to another, can offer good opportunities for what's called line packing in the pipe. At the other end of the scale, if you are fortunate enough to want your storage over the top of a salt deposit, that's probably a very good solution. Solution mining, salt caves is certainly a known technology, and there are a few around the world. There's at least one in Texas that's being used for hydrogen storage. The other two images there, the one on the right, that's of a lined rock cavern. They're starting to build some of these in Sweden. And essentially, they're mining out a cavity underground and with conventional mining methods, and then lining it and using the surrounding rock to take the pressure forces. Up above, we've got the depleted hydrocarbon well and or aquifers that other people are working on. There's still a lot of research to go into that. Probably contamination is one of the things that is going to be a problem, I think, for particularly green hydrogen storage, since you're making ultra pure hydrogen and then putting it in a natural reservoir that's not sealed from anything. So these are all good for, maybe 1,000 tons. You wouldn't bother developing a project like that for anything less than 1,000 tons. So there's a massive gap in the market, and that's where our company is sort of coming into the market. We can sort of close this gap in between. And like all of the storages on the right-hand side there, we rely on the natural strength of the surrounding rock structure to contain the pressure forces. So that way we don't need to build heavy-walled pressure vessels to contain the hydrogen. This is a graph, it's almost a graph of that previous image, but it just sort of helps to put into perspective the sort of size of the task that we're looking at. The X scale is logarithmic, so you can see up to about 10 ton. We've got plenty of these examples of pressure vessel storage. They're all the elements to the left there, and the scale on the Y scale is specific cost per kilo. So it's not surprising, I suppose, when you have larger scale storages, you get lower specific costs. So then we start to think about compressed gases in general and specifically hydrogen, but the leading cause of incidents with pressure vessels is caused by impact. So that's, the excavator digging into a pipeline or a truck running over a cylinder or something. So with our design, we put it in underground where this can't happen. The second most common is human error, and that's about when people are servicing valves or burst discs and elements like that. Because hydrogen does leak a lot, they tend to perhaps not necessarily follow the full procedures. They may, there's plenty of incidents we can look at where human error has been involved in perhaps not following quite procedure properly. That's caused a problem down the track. So if we have fewer interfaces, there's less risk of that. If you're going to combust hydrogen or it's going to burn in any way or explode, you have to have both an oxidant and an emission source. So storing it underground where there's no air surrounding it makes a lot of sense. You can eliminate that issue. And finally, on the safety side, exclusion zones are really important. So if you've got a whole bunch of above ground tanks, you have to have separation distances so that you're not propagating from one tank to another and causing a bigger problem. So with this design, the propagation would always be vertical. Just general design for hydrogen storage, you need a large scale. As I mentioned earlier, it's a very small molecule, and its energy content at at atmospheric conditions is quite small. So you still, even though you're compressing it, you still need a fairly large volume. It does want to leak through most mechanical seals. So the fewer seals you have, the less leakage problem you're going to have. Again, with pressure vessels, you need very high strength materials, which sometimes aren't compatible with hydrogen. And so, again, if we can take advantage of what is naturally underground, it helps us to contain the thing. And of course, these days, reducing visual impact and conserving space is always going to be important, especially if you look at facilities that are located in ports and things like that, where we think we're going to need a lot of hydrogen storage. This is a photo of an ammonia nitrate plant, and there was a case study done here in Australia where they currently use grey hydrogen. They form natural gas. We didn't do the study. It was sponsored by one of the local government agents here, and the long and the short of it is that to change this facility to a green hydrogen facility, so they're going to make their own solar farm and then put electrolyzers on. They required 50 tons. It was 54 tons of storage. So that would see them through, I think, about 95% of the time they could keep the plant running. And that was an acceptable outcome. So with available storage technologies, that they weren't able to use a salt deposit or anything like that. They could select, for example, about 50 of these 1-ton vessels and pair them up and take up a lot of space and a lot of interconnecting pipe work. Or on the other hand, we could just put in one of these underground units to take up obviously a lot less space and be considerably more safer. So I think, the safety issue is really important for our industry. We still hear horror stories of things that have happened in the past. So, everybody is going to need to really discuss safety as a priority. We're going to need large capacity. We're going to need lower cost. And obviously, if we're making really pure hydrogen from electrolyzed water, it needs to be returned in that state. There'll be plenty of applications where small footprints in really important. So yeah, just to summarize, the renewable energy is intermittent. If we're going to use green or renewable energy, we're going to make green hydrogen, we're going to need to decouple that from the demand. It's a very growing market. It's a new market because, as I mentioned earlier, previously all hydrogen was made on demand, more or less, apart from a very few niche applications. But so the hydrogen storage market is going to be large. We're going to advocate underground is going to have better cost and safety outcomes. And of course, you need a liner there to make sure you get back pure hydrogen from, if you're going to produce really pure hydrogen, you really need to get that back to avoid contaminating things like catalysts in your fuel cells and so forth. So I will leave that there just for your information. That's an image of one of the sites where we've used this technology for manufacturing vent shafts. So the liners you see there aren't the hydrogen liner, that's for a ventilation shaft, but it's the same technology we use. Okay, I'll hand it back to you, Christina.
Okay, well, David, thank you. Thank you so much for this overview. There's a couple of questions for you if you want to take a look at them. If not, we can do it at the end of the presentations. But thank you so much for yours. It was really good, and I think it's great to have this overview of the industry. So moving now, we're going to go with Sean. Sean, whenever you're ready, if you can share your screen. Perfect. Sean, you're on mute. Sorry, I couldn't see you.
Good morning from Texas, and howdy from Texas A&M. I
Howdy.
hope you'll have a good time wherever you are. My name is Sean Niknezhad. I got my PhD at A&M, and I'm a postdoc right now here. A mechanical degree background and energy and master's, and then PhD dual in business. David talked about underground storage, and they have a very nice technologies. It's a bright future for these kind of technologies. I'm gonna make you more familiar with onboard hydrogen storages and different technologies as we go. How can we store the hydrogen in general? You can store it in physical base, compress it, liquefy it, or you can use storages within the solid or surface of the solid, basically. You may heard of metal hydride, which is pretty big topic for onboard hydrogen storages, or even you can use reforming and storing hydrogen in shape of CH or any other source of chemicals that can store hydrogen. For the compressed gas, you need a high pressure tanks, and that's the issue, biggest issue, 350 bars or 700 bars of the tank. Or for and safety issues, you need control systems. You need to have specific valves, and then the materials to create those cylinders and compressors is very important. And for liquefaction, you need minus 252 degrees Celsius. It's pretty high. And as we go, I will go through some numbers. Right now, there are for onboard hydrogen storages. There are different automation industry, if you will, vehicles and companies investing into this. Hyundai, Toyota, they have invested a lot. Kia is now investing a lot. Ford is investing a lot. Chevron is doing the same thing. And if you look at the cost for 700 bars, you can for 500,000 units, you can look at $15 per kilowatt hour, roughly. 300 bars would be $13 per kilowatt, and on this table we can see the rest. There are some challenges here. The density of hydrogen is very low, so you would have leakages and lots of evacuation when you liquefy the systems, and typically you need a large volume because hydrogen is valuable by mass, not by volume. So as you have more mass into your system, then it will be more valuable. And at the end, any kind of systems you use for hydrogen storage, you have to have some sort of refilling systems. You have to inject the hydrogen into it in some way. And that system needs to be safe, quick, and easy to do it. For example, if you're using liquefaction processes, when you do refilling, the temperature needs to be between minus 20 degrees Celsius to minus 40 Celsius. To just do the refilling system. That's very important to go to the right direction. Look, you know, hydrogen by energy has more energy content than methanol, methane, you know more than me on this. But when we look at the energy costs on that, for 10,000 PSI, you're looking at a 4.5 kilowatt hour per kilogram for 700 bars. And in case of energy, cost for 5,000 PSI, you're looking at 3.3 kilowatt hour per kilogram of hydrogen at gasification process, 350 bars. Liquefaction is more expensive. You would look at $10 to $15 kilowatt hour per kilogram. More challenges are involved here, though. The material for any of these, the material you would use to create the either physical base or material, the steel materials are expensive. Thermal management is very important. Having the right control system through your system in any of this is very important. You have to control the pressure, you have to control the temperature, and sensors are required. That's what we do here a lot, control systems. How can we control the temperature and pressure while you do refilling the tanks or any other sources, even in in solid absorption or adsorption processes. Tank mass, the mass of the tank is very important also. But the efficiency is very critical in all of these processes. You can take a look at the graph here and see the different challenges. The purity is important when we talk about hydride or chemical hydrogen storages also. Again, in the last 10 years, these are the main companies have developed valuable products and trying to commercialize what they do. If you can see it from Birmingham in England, they have done some stuff to the United States, all around the world. You can see it for forklift trucks. There are many different stakeholders now involved in developing hydrogen storages right now. This is one of my babies, actually, is for metal hydride. You can see the system. So in this system, we use water as a cooling system. You have temperature sensors. We have developed a control system to manage the temperature here. And water would be also another component to control the temperature. And this metal hydride can be used for heavy vehicles industry. That's our goal. You can use it for fast trains. You can use it for heavy trucks. And you can look at the hydrogen storage material database by Highmark. The consortium has been made for material database on this specific one. When we talk about a compressed hydrogen storages, different composites and metals are involved now. What we like is to create one from all composite construction. That's the most valuable thing we can do. Unfortunately, the pressure can go high to 70, and then the gravity density would be 5.2 to 5.7, which is higher than any other type of tankers, but it's very expensive. $633 per kilogram of hydrogen. If we do it with metal, the cost would be $83, but the gravimetric density would be 1.7, which is much lower. So if we can bring down the cost of composite construction, and even for undergrad usage or any other sources, you would have more mass into this. But if you can bring down the cost, and that's what we need in the future. When we look at the Type 4 cylinders for compressed gas, if you look at 10,000 system per year capacity, you're looking at $22 per kilowatt hour. And if you look at 500,000 systems per year, you're looking at $15 per kilowatt hour. And you can see the different materials can be used. Carbon fiber. Carbon fiber is one of the things that can help the climate. You would reduce the CO2 production at your refineries. At the same time, you can benefit from high quality, and your approach would be toward all compositions because it's not a metal base. Carbon fiber is one of the good things we can mix with our tankers for compressed gases. Liquefied hydrogen, you can see the prices here. The issue is you have to bring down the temperature to 20 Kelvin and then about 5 atmospheric pressure. That's one of the issues. But when we look at the prices here, above 10,000 kilogram of mass of hydrogen, the liquefied is much less expensive than other liquefied processes at high pressure even. What are the pricing factors we think when we talk about a hydrogen storage, a technology and storage type? Energy prices in that area, capacity and scale you're doing this, the utilization rate you do, the location infrastructure, how many companies are around providing those services to you, and then the cost of operation that has a very direct relationship to your area operating, the market supply and demand, where you're located at England. Most of countries now trying to working with hydrogen. Don't forget this. Hydrogen is an energy carrier source. At the same time, is a mother of many chemical productions, polymers, ethylene, propylene, all of those. We need to add hydrogen through the system to make those polymers. So hydrogen by itself is very important, valuable product, and finding cleaner way to produce that hydrogen is very important too. Incentives is another case that in many countries now helping hydrogen industry. And the level of arguments you create, and then the competition you have around and technology advancement. If you look at the levelized costs I have here, we can say that, okay, if we have a liquid hydrogen above 10,000 mass is valid number for us to create a liquefied system, and below 100 is good for gases with a 20 kilogram per cubic meter mass volume. So it depends on your scale. You have to choose what is the best technology to implement in your area. There are different standards right now running around. 46 is under revision, but right now the most important one is the ISO TC 9197. You can see this for vessels, you can see this for pressure vessels, pipelines, metals, you can use this and that. And pay attention, it's different from the country to another country. For Japan, United States, and Europe, they are different. Even Iceland has their own regulation that is accepted by the government. And this is my baby, actually. One of the components that we have, we can reduce the cost of storing hydrogen and the way we produce it. Some areas don't have enough water to produce it. So in this case, we use natural gas and a plasma technology using renewable or any kind of resources, even the grid. But as you get renewable energy to your system, you get most incentives, and then by the carbon intensity of $3, since this technology has zero direct CO2 emission, you would be qualified for $3 per kilogram of producing hydrogen. So the only thing you will pay is the hydrogen storage when you're applying this technology to your technology. On my video, you can see that how we can reform natural gas to hydrogen immediately. I'm telling, we reform more than 30% in less than 10 nanoseconds. It's a very fast process. It's a non-thermal, and you can do it at ambient pressure, ambient temperature. That would help you to reduce storing the cost of storing your hydrogen. And you can benefit from different business models. It depends on what you do. You can store the hydrogen. You can sell it as a service. You can sell it back to the grid. In Texas, in West Texas, we dump about 60, some days we dump about 60% of electricity, because economically it's not feasible to transport all those electricity from east to west. So they dump it. What if we use that energy to produce, and we have lots of flaring gases also and natural gases, right? So what if we use those electricity to reform natural gas to hydrogen and store it as a hydrogen energy source? Transport and delivery services is another way you can be involved in this business. Leasing, maintenance services, consultants, grants and incentives you can benefit, and trading of this carbon trading or hydrogen trading, all these kind of businesses you can make around. I'll be happy to answer any question. I try to go fast, and we answer more questions than I just only talk to you.
All right, Sean, well, thank you so much for that market overview and for showing us your baby, which I'm sure. Does it keep you up at night? Does it cry? And
Two of them, yes, they're ready. They're ready. We like to go to the pilot size now, testing.
Wow. All right. Awesome. Well, thank you so much for this presentation, and thank you everyone for all the questions that are coming up. So I'm going to start with a couple that David already highlighted. We had pre-submitted questions, but I think since we have tons of questions by the audience, we're going to delve right into these ones. And David, we're going to start with one from Roxana, which talks about underground storage of hydrogen seems to be a challenge, and I particularly am concerned about containment. Would it be better to target store it as ammonia or other, as you suggested at the beginning?
Okay, thanks for that question. I think the answer is there will be different sorts of carriers for different applications. So if you want to use ammonia in your process, you would probably store it as ammonia. I'll back that up one step though. Prior to the way that ammonia is made is with hydrogen, and you add in the nitrogen. And so this process is called the Haber-Bosch process, and it needs to run continuously. It can't sort of ramp up and down. So you need a constant supply of hydrogen. And so our proposition is that if you're going to use green hydrogen, you would need to have that stored prior, because the intermittent energy that drives that green hydrogen is not reliable. And so that case study I did was a perfect example of that. The green hydrogen that's used in the ammonia nitrate process is stored on site so that the harbour wash process can continue indefinitely.
All right, well, thank you, David, for that answer. And Sean, if you want to pop in, just let me know. The same David, while we ask questions directed to Sean, if you want to also intervene, please just let me know, and we'll give you the floor. Well, thank you for that question, Roxana. Next one, moving on. Sean also mentioned one of our questions from Batu Varlik. So the question is, what is the expected maximum time for hydrogen storage, and what is the equipment to provide this time?
It depends what type of technology we use. Do we store it within the solid or the surface of the solid? That would change the timing. Of course, if you do compressed and liquefaction processes are involved, those are different too. But what I can say, even within the solid, it's a pretty fast process. The issue, if we talk about within the solids, it's about the capacity. How much can we store? When we talk about a compress, that's a different story. Liquefaction, you can store as much as you like. As I said, more than 10,000 is good. But timing is not the problem. Doing it safe is more matter. So having the right control system in place would assure the safety. And as you assure the safety, you can do it minus 20 degrees, and minus 20 degrees is pretty good temperature to do it for us. So there's no issue with the timing. The matter is how we can control the pressure and temperature. Playing before injecting it in any of these solids or cylinders, if you could control the temperature and pressure, you will control the velocity and the timing, and that depends on your capacity of the storage. Timing is not a problem. That's the bottom line, actually.
I might just add to that too, that if you are storing hydrogen, you can store it as the molecule anyway. I'm not too sure about in the hydrides and other methods, but as a compressed gas, it virtually stays as hydrogen until you need it. So from the longer term, you can store it very long term.
All right. Well, thank you so much for those answers. The next question is directed to both of you. And it's, what do the panelists from Jerry Hollisay, what do the panelists think about the potential for marine transport of compressed hydrogen for distribution by pipeline? If any.
I'll go
There doesn't have to be an answer, but just.
I think the issue comes down to, as Sean was saying earlier, the mass you can get in to a fixed volume. So it's going to be, I think most people are talking about liquid or another carrier such as ammonia for marine transport over long distances. There could be niche applications where you have a fairly short distance that you would need to do the economics of whether the cost of liquefying it and then regasifying it is worth that versus the amount you can put in. So what I'm saying, for a small sort of coastal or littoral type waters, it may be okay, but I think generally for long distances, it would be a liquid or another type of carrier.
Okay, thank you. All right, well, next question marked by David is from Michelle Detwiller, and she asks, how far underground are the tanks buried? Is it suitable for locating where the hydrogen is issued? If the answer is yes to the second question, aren't you still needing to transport hydrogen from point of production to the underground tank?
Okay, so to take the first part of the question, the depth of the tank is going to be a function of how much storage you want. So we've got experience drilling shafts down to 600 meters deep. So we may not go that deep depending on the type of rock that we encounter. It's probably unlikely for a hydrogen project we would want to go that deep, because you start to lose drilling rates And we have a 40-meter cover thereabouts at the top to keep the tank in, the shoulders of the tank supported by the ground above it. You can use it at either end or along a pipeline. So indeed, you could locate your storage at where the hydrogen's produced or where it's demanded. We've looked at different projects where different applications require storage at one end versus the other. The nice thing about having it stored where it's used means your pipeline can in fact be smaller, because you can run your pipeline for the velocity of your electrolyzers, and then have a smaller storage at the other end. So it depends on the application, but yes, you still need to transport it. If you're going to use it on the site, you manufacture it.
Okay, well, thank you, David, for that answer. Moving on to a question from Patrice Horner. Sean wanted to answer it. The question is, awesome tech. Is the plasma tech energy intensive versus electrolysis?
The answer is yes. You get the full incentives because the direct CO2 emission would be zero. And here's the point: if you talk about the United States, you have to be qualified as a renewable electricity producer, and that plan needs to be made by 3 years. And so it doesn't matter really, because we can get it from renewables, and even for water electrolysis, you can get it from renewables too. If that facility that provides electricity satisfy that 3 years, both of them can get the incentives. And then on both cases, the direct CO2 is zero. Scope 1 and Scope 2 are regulated in the United States. Scope 3 is not regulated in the States. So in that cases, yes, both of them getting all the incentives. And about energy intensity, if electrolyzer is using 50 kilowatt hour, our case is 8. So we are 1/3, and we are sitting at $3 about it, and electrolyzers are sitting at 5.5. So considering even those incentives, that $3 I mentioned, we are sitting at about $0 to $1, and for water, you would see it about with the incentives and everything, you would see at $4.
Okay, thank you, Sean. So moving on to another question David wants to answer from John Kopas is, what hydrogen pressure does the Ardent board shaft storage support?
Okay, so the pressure would be optimized for the particular application. We will be offering about 250 bar in any sort of rock type. And there might be applications where we would go higher. The 250 bar is settled on mostly because of what the compressor guys are telling us is pretty easy for them to handle. It seems to make a lot of sense with customers we're talking to for them to either let it down for a further process, or put it in a pipeline, or even to boost it up for a mobile application. So it depends after we do our geology and our design exactly what pressure we can take. It's going to be a minimum 250 bar.
Okay, well, thank you, David. Another question that you wanted to answer is by Steve Bissett, which is, what is the liner material?
Okay, I think there was another question very similar to this, so I'll answer them both together.
Okay.
The liner is a composite that we've actually patented the design of the liner. And what it does is a number of things. Firstly, it obviously contains the hydrogen, stops it leaking out into the formation. The second element is it needs to have enough strength to stop the crash force from the hydrostatic head within the formation. The third thing it does is we have a second chamber in it that contains a working fluid that allows us to put it in different rock types to allow the deflections within different rocks as we go down and the jointing. And so within that, we have a fluid in the second chamber that matches the pressure in the first chamber, and this relieves any stress on the liner that faces the hydrogen. Therefore, we avoid the embrittlement issue. There was also a question about leakage, and this working fluid is a element that allows us to detect leakage within that fluid. That's where it will transfer, and we can detect it at the surface.
Okay, thank you. All right, Sean, there was a question for you from Rajesh Kumathikar. If you could explain a little bit or go a bit more in depth in your presentation, why the cost of hydrogen storage is declared in dollars kilowatts. Can you explain this a bit more in detail? Oh, you wanted to answer it. Sorry, I didn't see that. If you could explain this a little bit more.
Sure. That cost, the one I mentioned, $22.94, is just specifically for type 4. We have different types of cylinders, if you will. So that one is specifically one type, which is type 4, plus what is the usable hydrogen into your tanks. That one is using 5.6 kilogram. So as you change these numbers, you would your number would go high a dollar or so, and then go down a little bit. But that number is very accurate, and that's why you saw $1 or $2 differences. That one is 5.6 kilogram of usage based on the DOE vision. They aligned, and then the second thing was it was based on 10,000 systems per year, and then 500K system per year. That's why it was $1 off there. It's bigger production by scale.
Okay, thank you for that answer provided, Sean. Next question, David, that you wanted to answer. Well, it's one of the ones in the beginning that I skipped. Sorry about that. It says, David, that on slide 4, may the current pipeline not be used for hydrogen. Could you explain to Varlik a little bit more what it was meant to be, or give us a bit more explanation?
Yeah, so it depends on the material of your pipeline. Most pipelines are constructed with a high tensile steel, and the hydrogen reacts with these types of steels. And so you might be able to use that pipeline, but it's at a significantly reduced pressure. And then we get back to the problem of it's the volumetric amount of hydrogen versus the mass that you've got in the hydrogen. You can't transport the same amount of energy in that pipeline, certainly not at the same pressure. And therefore, that's what sort of is problematic. But I'm not saying you can't transport it in steel pipelines. People do it all the time, and there will be a requirement to do it. It's just the existing pipe network won't be able to have the same capacity as it does for natural gas.
Okay, thank you. All right, well, moving on to a question from Michael Hoghuki. This is for both of you, which is where are the sweet spots for hydrogen usages applications today? Sean, do you want to start?
Yes, so hydrogen, we have to dig into more. So hydrogen is not just an energy resource. It's, as I say, it's a modern molecule. Any kind of petrochemical production needs hydrogen. So even if you continuously commission the plants that we already have, refineries, instead of using SMR for 1500 Fahrenheit temperature and then 3 to 25 bars of pressure, what if you adopt new technologies for producing hydrogen or syngases even at a more friendly environment? So that's a huge question from 100 years ago. When we talk about the future and truths, the IP doesn't belong to the United States. First of all, we adopt even Haber-Bosch. They are not, they made in Germany for about 100 years ago. So how can we really change the technologies for a modern 21st century and producing hydrogen in a cleaner way? And then as you have hydrogen, you need to store it too. So this is a different setup. This is a different concept than what is a new demand. So in case of past, we have to have a cleaner system for producing hydrogen because we need, at the end of the day, we need to produce hydrogen. That's one thing. The second thing for the new demand on this on the demand side, there are different conversations now. Adding 30% hydrogen to natural gas pipeline is one scenario. United States, they are following to have more hydrogen through the pipeline and less carbon through the pipeline. So we make the combustion process more cleaner when we combust natural gas. Having liquid ammonia in future is for maritime and other purposes is another demand for hydrogen. And another thing, another component is how can we store the base electricity? How can we store in a more efficient way the electricity? That's the third demand that we are looking at now. But in my opinion, first comes first. How can we produce the hydrogen in a cleaner way? How can we store that hydrogen? We haven't answered this question yet, in my opinion. We try to answer.
Thank you, Sean. David, do you have anything you would like to add?
I'd just probably echo what Sean was saying. I think the early wins for hydrogen applications is to displace the steam methane reforming process. It's a very dirty process. Currently, in the world, we produce about 100 million tons of hydrogen per annum. 99.6% of that is made with steam, from fossil-based fuels. If we could displace that, that's a gigaton of CO2 saved. So I think that's obviously the first place to look, where they already need hydrogen.
Okay, well, thank you very much. All right, next question is from Azar Masood for Sean. Well, Sean wants to answer it, but please feel in to dive in, David, if you want to add something. The question is how far the plasma technology is in terms of commercialization.
So we are trying. So it's been made at industrial scale at the lab. So 3 liter per minute is the feedstock, which is good. It doesn't need to the chamber for reforming doesn't need to be bigger. We just add more units. So we are ready to take it to the pilot size testing, and that's where we are right now. We're fundraising for pilot tests.
Okay, thank you. Question for David from Batu Varlik. I understand that storage and transfer of hydrogen requires specially designed tanks and pipelines. So this makes the current natural gas or LNG one unstable. And this will make another problem in our path to adding new greenhouse gas emissions. Can you please give a little bit more detail or share your opinion on this?
Yeah, I think I sort of touched on that a little bit earlier. The existing natural gas pipeline, depending on the materials, again, here in Australia, most of our pipelines are made out of high tensile steel, and they're not going to be compatible. So, yeah, I think that it will require new infrastructure, but our value proposition is more that we can locate the storage either where the hydrogen is produced or it's needed. So that way you can optimize the size of this pipeline. You don't necessarily need to have a very large pipeline. And indeed, there's many projects we've looked at where they've had their storage located separate. So I'll give you an example. Your solar farm, wind farm might be inland, yet you want to export ammonia. You would generally build your ammonia plant on the coast. And then the question is, do we have a large pipeline at one end, between the two, or do we go for a smaller pipeline and have storage at one end or the other, or both? And so that's sort of the trade-offs, if you like, and it comes down to economic decisions, really. And large pipelines are very expensive.
Okay, thank you. David. A question from Dean Tomic is, if you can't transfer hydrogen via existing pipelines, can you transform it to liquid ammonia prior? Sean, would you like to answer this question?
Well, this is the $1 million question. It depends what country do we talk about. Most of the pipelines, at least in the United States, belong to the utilities company, and utilities company burn natural gas to produce electricity, so they have to find reasonable reasons to move from natural gas to ammonia. Moving the hydrogen in a mass scale is not a problem, in my opinion. It's about the momentum we need to create to make this happen, as far as I know, and we are involved. There's a $7.2 billion investment in the United States to create different hydrogen hubs. One would be in Texas for $1.2 billion. And I would say after, if the state and the government start constructing the facility, we would see more movement on the pipeline size. Changing it from when we talk about ammonia, we need a air separation facility to take the nitrogen out of the air, and then combining that with hydrogen and producing ammonia, which is good for maritime, in my opinion. And we are not yet ready in the United States to use ammonia in case of, because it's like diesel, in my opinion. It's a very nice diesel. We are not yet ready, at least in the United States, to move toward that very fast. We need more time, but I can see it more in West Europe.
Okay, well, thank you very much. All right, and one of our last questions, David, I see that you're writing it down. Do you prefer to answer it? Oh, you already answered it, I think.
Which one was that? Sorry.
Oh, yes. Does the compressed hydrogen flow rate into the Ardent tank matter? You said yes from a temperature perspective. All right, perfect.
Yes, I'll just add to that. We've got it live. There's materials involved that need to be kept within certain temperature limits, and if you fill really, really fast, you're going to heat the storage up. As I mentioned earlier, we have a working fluid in a second chamber around the tank, and we also use that to control the temperature, so we can exchange heat with the tank back to the surface, and then reapply that heat later when we're letting the tank down. So.
Okay, well, thank you for that detailed explanation. And our time's almost up, so thank you, David and Sean, for being in this webinar. It was amazing having you here, so thank you so much. And thank you everyone else for coming and joining. We had over more than 120 people. I'm checking, and amazing questions, so thank you so much. I'm sorry we couldn't go through all of them, but we did cover a couple of them, so that's pretty good. We hope to see everyone very, very soon in one of our coming next webinars, and everyone have a great day, or if you're with David in Australia, a great night, or what's left of it. Thank you everyone for joining.
Big pleasure to be here.
Thanks a lot for having us.